Swayam Prabha. Digital India. Educated India.
Welcome to lecture 39 on time series modeling and forecasting. In ALMA processes, we mainly study how the mean of the process has evolved. In fact, if the process is stationary, then the mean of the process is constant. But if you consider the conditional mean, then it depends upon the past observations, conditional mean given the past information. For example, if you consider AR1 process, yt equal to 5 yt minus 1 plus ut, then expected value of yt given the past observation, say yt minus 1, yt minus 2, so on, is equal to 5 yt minus 1. So, it tells you how these conditional expectations have evolved. This process tells you about the evolution of conditional expectations or conditional means. Now, the same thing one may think of the variances also. For a stationary process, the variance is constant, but one may be interested in how the variance has evolved. This conditional variance may vary with time. Now, one phenomena which has been often observed in time series is that if there is a big change, a large change, it is normally followed by a large change. That change may be increase or decrease, may be positive or negative, but usually it is followed by several shocks or several large changes, and this kind of behavior often leads to some kind of clusters in variability. In some portions of the time series, you find a lot of variability. If there is a normal change, it is usually followed by a normal change. But if the magnitude is large, then it is usually followed by a large change. That large change may be in the same direction or in the opposite direction. Now, this kind of volatile behavior may be of interest to many applied workers, may be for many economists or for many people who are working in the financial market. Say, for example, if you know that the share prices have this kind of volatile behavior, then you can take advantage of this kind of volatile behavior, or you may lose a lot of money because of this kind of volatile behavior. If you enter the market at the right time, if you have some idea of how this volatile behavior is going to work, then you can gain a lot. And if you do not have any idea, if you are not analyzing this volatile behavior properly, then you may lose a lot of money. So, people may be interested in this kind of volatile behavior of the time series. In this lecture, I am going to consider some stochastic volatility models. In particular, I will consider arc and Garg models. In this lecture, I will consider arc models. In the next lecture, Garg models. So, we come to arc and Garg models. Then ARMA models describe the mean development of time series. Then optimal forecast is the conditional mean of the model, which minimizes the forecast error variance. Again, the unconditional variances are time invariant. They are constant, don't vary with time. But the conditional variances and covariances often depend on the magnitude of past shocks and past variability, just like this conditional mean of the model. This conditional mean depends upon the past observations and the past shocks. So, the conditional variances also may depend upon the magnitude of the past shocks and past variability. Then in modern economic theory, increasing role of risk and uncertainty considerations makes the modeling of time varying variances and covariances crucial. So, the study of changes in model variability may be of interest to many economists or many people who are working in risk analysis or financial market. Now, modeling and understanding nature of temporal dependence of variances is important for many issues in macroeconomics and finance. So, how the variances change given the past shocks or given the past variances. This kind of dependence may be of interest in many fields. And if you are estimating the forecast error or forecast error uncertainty, then a much more accurate estimate of the forecast error uncertainty is possible by conditioning on the current information set. So, if you know that any large changes lead to large changes in next period also. So, if there is a lot of variability, then it is going to lead to a lot of variability in the next period also. Then accordingly, you may modify the forecast error uncertainty. Then financial data show volatile behavior. Often these data show volatile behavior. Then the risk associated with an asset or investment is crucial factor in modeling financial data. And what measures that risk? Measure of risk associated with the asset is asset volatility. How much volatile behavior the asset price has or investment has. Now, let us take some examples of real data set which show volatile behavior. Now, this is the graph of VIX historical price data from 3/1/2006 to 14/12/2007. Then you observe that here the time series is behaving normally, then there is a sudden increase, and after that it is followed by a lot of changes. Then again there is a sudden increase, then you get a big decrease, and it is followed by many changes. Or at this point you can observe the volatile behavior. So, there is an increase, then suddenly the time series is decreasing, again it increases, decreases with big magnitude, and ultimately it reaches here. So, this period is called built up. The volatile behavior is building up. Then this is the volatility event. Then you have normalization deflection. It is going towards the normal situation. So, this kind of behavior of the time series leads to many variability clusters. Here you get a cluster of variability, again you have a small cluster here, here you have a big cluster. Then this is the time series of daily changes in Wilshire 5000 stock index. It is a time series of daily data from 14/9/2016 to 14/9/2021. So, this is very recent data. Then you observe that the means here time series is behaving normally, then you have some volatile period here, and then you have a big volatile period here. Then we have time series of South African real gross domestic product. So, this GDP data also shows a lot of volatile behavior here. Now, this is a statement given by Mandelbrot. Large changes tend to be followed by large changes of either sign. If there is a large increase, then in the next period you may have a large increase or large decrease. It may be of either sign, and small changes tend to be followed by small changes. And if your time series has this kind of behavior, then it is going to form different clusters of variability. Whenever there is a large change, you get a cluster, you get lot of changes, lot of volatile behavior in the time series, lot of changes in both the directions, increases, decreases, then increases, etc. So, you get different clusters. Then volatility has these properties. There exist volatility clusters, that is, volatility is high for certain time periods and low for other periods. We have considered different examples here. It is low for some of these periods, then it is high for this period. So, you get this kind of volatility clusters, or in this example also you have different clusters. Then volatility evolves over time in a continuous manner, that is, volatility jumps are rare. So, it is not like that you get volatility jumps everywhere, these are there. Then volatility is often stationary and does not diverge to infinity, it varies within fixed limits. So, although the time series has volatile behavior, but that variability is usually stationary, it does not diverge to infinity, and the variations are within fixed limits. Then volatility seems to react differently to a big price increase and a big price drop. So, usually the big price drops usually having a greater impact. So, both these events have different kind of impact. A big price increase has different kind of impact, a big price drop has different kind of impact. So, it may not be symmetric, and usually the big price drops have greater impact. Now, this phenomena is referred to as leverage effect. Then the consequence of this kind of behavior is OLS is best linear unbiased estimator and consistent, but if you have volatile behavior or if the conditional variances is varying, OLS is no longer efficient, say minimum variance. In particular, if you are also considering the non-linear estimators, then the OLS are not efficient. Volatility model. Suppose YT is the log return of an asset at time index t. Then series YT is either serially uncorrelated or with minor lower order serial correlations, but it is a dependent series. So, we assume that YT is serially uncorrelated, or even if it is serially correlated, it has very minor lower order serial correlations. Then the conditional mean and variance of YT given Ft minus 1 is Ft minus 1 is the information set up to time t minus 1. So, say mu t is equal to expectation of YT given Ft minus 1, and sigma square t is equal to variance of Yt given Ft minus 1, or this is equal to expectation of Yt minus mu t square given Ft minus 1. So, Ft minus 1 is the information set available at time t minus 1, and Ft minus 1 consists of all linear functions of the past returns or past observations, you can say. Suppose Yt follows an ALMA PQ model, so that Yt equal to mu t plus ut, and expectation of Yt given Ft minus 1 equal to mu t is equal to phi naught plus summation I equal to 1 to p phi I Yt minus I minus summation j equal to 1 to q theta j ut minus j. So, Yt follows ALMA PQ process. Then sigma square t is equal to variance of Yt given Ft minus 1. Now, if you obtain the unconditional mean of Yt, it is 1 minus summation I equal to 1 to p phi I, and this unconditional mean of Yt is independent of t. So, the process is stationary and its mean does not involve t, but this conditional mean of Yt given Ft minus 1 involves the past observations as well as the past shocks. Then conditional mean of yt given ft minus 1 evolves through interaction of past observations and shocks through this model. Similarly, the conditional variances may evolve through magnitude of past shocks and past variability. So, it may be possible, and if it is possible, then one may be interested in modeling these conditional variances using the information contained in the magnitude of past shocks and past variances or past variability. So, the conditional heteroskedastic models are concerned with the evolution of sigma square t. Just like the ARMA processes are concerned with the evolution of conditional mean of yt given ft minus 1. Then the manner under which sigma square t evolves over time distinguishes one volatility model with another. Then if you take sigma t equal to the positive square root of sigma square t, then it is called the volatility, and volatility measures the size of the errors made in modeling returns and other financial variables. Now, these conditional heteroskedastic models can be classified into two general categories. First is we use a stochastic equation to describe sigma square t, and these models are called stochastic volatility models. Usually these models involve some kind of differential equation, but in this lecture we are not concerned with, or we are not covering these models. The stochastic volatility models we are not considering here. The second one is use an exact function to govern the evolution of sigma square t. And the examples are autoregressive, conditional, heteroskedastic, or these are also called ARC models, or another form of models is generalized autoregressive, conditional, heteroskedastic, or GARC models. So, in ARC models actually we express the current conditional variance, say sigma square t, as a function of magnitude of past shocks. In fact, we take the square of past shocks. So, we express sigma square t as a linear function of square of past shocks, whereas in GARC models, along with the squares of past shocks, we also incorporate past variances. So, GARC models involve both the squares of past shocks as well as the past variances. But ultimately the objective of both of these models is to investigate how conditional variability has evolved through the interaction of magnitude of past shocks and past variability. In ARC models, we are not considering the past variability, we are just considering the magnitude of past shocks, whereas in GARC models, we are considering both the magnitudes of past shocks as well as past variability. Model building, how we build a volatility model for the time series. So, model building involves these 4 steps. First, we specify a mean equation. Say, first you may test for serial dependence in data. If data are serially independent, data do not show any serial dependence, then you go to the next step. But if data show some kind of serial dependence, then you may build some time series model. For example, ARMA model or simple moving average model or autoregressive model, etc. So, we built a time series model, say ARMA model, we fit the model, and we follow this step just to remove any linear dependence. And once you fit a model, then you can again check whether your residuals are serially independent or not. So, once your residuals show insignificant serial dependence, then you proceed further. Then use the residuals to the mean equation to test for arc effects, whether these residuals have arc effect or not. And then we specify volatility model if arc effects are statistically significant, and we perform a joint estimation of mean and volatility equations. We estimate the mean equation as well as we estimate the volatility equation. Then we check the fitted model carefully and refine it if necessary. So, these are the broad steps for building a volatility model for a time series. So, first we consider the arc or autoregressive conditional heteroskedastic model. In arc models, the shock ut is serially uncorrelated, but dependent. So, all the UTs are serially uncorrelated, but these UTs are dependent. And then this dependence of UTs can be described by a simple quadratic function of its lagged values. So, suppose we consider arc M model, then arc M model assumes that we write ut equal to sigma t epsilon t, and this epsilon t is a sequence of IID random variables with mean 0 and variance 1. Then we write sigma square t is equal to alpha naught plus alpha 1 ut minus 1 square plus so on plus alpha m ut minus m square. So, basically in this arc model of order m, what we are assuming? We are assuming that sigma square t, the current variance given the past information, depends upon ut minus 1 square, ut minus 2 square, so on up to ut minus m square. or the magnitude of past shocks up to lag m. So, then here we assume that alpha naught is greater than 0 and alpha I is greater than or equal to 0 for all I equal to 1, 2, so on. Then alpha I satisfies some regularity conditions to ensure that the unconditional variance of ut is finite. So, some regularity conditions must be satisfied. Then epsilon t is assumed to follow the standard normal distribution or a standardized student t distribution or a generalized error distribution. So, usually one can think of a standard normal distribution. You assume that epsilon t follows standard normal distribution. But what happens in our models? The errors are usually lactokurtic, means the errors have fatter tails, fatter than the normal distribution. So, often to model the errors, one prefers to use a distribution which has fatter tails than the normal distribution. And two such distributions are a student t distribution and a generalized error distribution. So, people also use these two distributions as the distribution for epsilon t. Then under the arc framework, large shocks tend to be followed by another large shock. That large shock may be positive, means increasing, or it may be decreasing. But usually a large shock is followed by another large shock. Now, to investigate the properties of arc models, we consider arc model of order 1, arc 1 model. So, for arc 1 model, ut is equal to sigma t epsilon t, and sigma square t is equal to alpha naught plus alpha 1 ut minus 1 square. Alpha naught is greater than 0 and alpha 1 is greater than or equal to 0. So, if this ut minus 1 has large magnitude, means u square t minus 1 is large. Now, alpha 1 is greater than or equal to 0. Suppose alpha 1 is not equal to 0, it is greater than 0, right. So, a large value of ut minus 1 square leads to, this implies a large sigma square t. Means there after a large value of ut minus 1, a large value in magnitude of ut minus 1, there is a possibility of large variation. So, there is a possibility that a large shock in magnitude is followed by another large shock. It may be in the increasing direction or in the decreasing direction, but since sigma square t is large, so there is a high probability that a large shock is followed by another large shock. And basically what is your objective? You want to model this phenomena. You have observed the phenomena in your time series that a large shock is followed by a large shock, and you want to develop a model for this phenomena, a model which can accommodate this phenomena. So, you have used this arc model, and this arc model also has this phenomena. A large shock in magnitude followed by another large shock. So, this arc model can be used as a model for this kind of volatile behavior. Now, if you take expectation of u t, then first we take the conditional expectation of u t given f t minus 1, then conditional expectation of u t given f t minus 1 is equal to sigma t expectation of epsilon t, and this is ultimately equal to 0. Then variance of u t is equal to expectation of u t square. Again, in fact, the result which we are using here is like this. Say, suppose you have two random variables x and y. These are two random variables. Then the unconditional expectation of y is equal to, suppose you take the conditional expectation of y given x first. And then you take the expectation over x here. So, the expectation over x, the conditional expectation of y given x gives you the unconditional expectation of y. This result we have used here. So, variance of u t is equal to expectation of u t square, which is equal to expectation of u t square given f t minus 1. This is the conditional expectation. Then from the arc process, you observe that expectation of u t square given f t minus 1 is equal to the conditional variance of u t given the information up to time t minus 1. And the conditional variance of u t given f t minus 1 is sigma square t equal to alpha naught plus alpha 1 u t minus 1 square. So, you get expectation of alpha naught plus alpha 1 u t minus 1 square here. Again you get this equal to alpha naught plus alpha 1 expectation of u t minus 1 square here. And then this is equal to alpha naught plus alpha 1 variance of u t, because this is unconditional expectation of u t minus 1 square. And since ut is stationary. So, its unconditional variance is constant. So, expectation of ut square is equal to expectation of ut minus 1 square. So, we write it equal to alpha naught plus alpha 1 variance of ut. So, you get variance of ut equal to, you take variance of ut towards the left hand side. So, you get 1 minus alpha 1 variance of ut equal to alpha naught, and this gives you variance of ut equal to alpha naught upon 1 minus alpha 1, which is greater than or equal to 0 as long as alpha 1 lies between 0 and 1. So, you require the condition on alpha 1. Alpha 1 must lie between 0 and 1, so that the variance of ut is non-negative. Remember, here we mentioned that alpha I satisfies some regularity conditions to ensure that the unconditional variance of ut is finite. So, here for arc 1 process, that condition is alpha 1 lies between 0 and 1. Now, we obtain the fourth moment of ut, and we assume that ut is fourth order stationary, and then we write m4 equal to expectation of ut to the power 4. So, we have expectation of ut to the power 4 given f t minus 1 equal to, now we have taken the distribution of ut as normal distribution. So, this result is actually valid only when ut follows normal distribution. So, if ut follows normal distribution, then for normal distribution, you know that m4 is equal to 3 times m2 square. Where m4 is the full central moment and m2 is the second central moment, or m2 is the variance actually. So, m4 is equal to 3 times m2 square. So, we write expectation of ut to the power 4 given f t minus 1 equal to 3 times expectation of ut square given f t minus 1, then we take square of this. Then expectation of ut square given f t minus 1 is equal to alpha naught plus alpha 1 ut minus 1 square, then you take square of this quantity. So, you get 3 times L square of alpha naught plus alpha 1 ut minus 1 square. So, m4 is equal to expectation of ut to the power 4 equal to 3 times expectation of alpha naught plus alpha 1 ut minus 1 square whole square, and then this is equal to, you take square of this. So, you get alpha naught square here, and since alpha naught is a constant, so its expectation of alpha naught square is also alpha naught square. Then you get cross product term 2 times alpha naught alpha 1 expectation of ut minus 1 square, which is equal to variance of ut plus alpha 1 square expectation of ut minus 1 to the power 4, which is equal to m 4. And then this is equal to 3 times alpha naught square plus 2 alpha naught alpha 1. We substitute the value of variance of ut, which is equal to alpha naught upon 1 minus alpha 1. Then we get plus 3 times alpha 1 square m 4. So, again you take this term towards the left hand side. So, you get m 4 1 minus 3 alpha 1 square equal to this term. And then you can simplify it, and you can easily verify that m 4 is equal to 3 times alpha naught square 1 plus alpha 1 divided by 1 minus alpha 1 into 1 minus 3 alpha 1 square. And this m 4 is also greater than or equal to 0. So, this implies that not only alpha 1 lies between 0 and 1, but 3 times alpha 1 square also lies between 0 and 1. Of course, it is greater than 0. So, there is no issue, but it is less than 1 means alpha 1 square is less than 1 upon 3. Now, the unconditional kurtosis is m 4 upon variance of ut square. Actually, kurtosis is equal to m 4 upon m 2 square, and m 2 is equal to variance of ut. And then we substitute the values of m 4 and variance of ut here, and ultimately you get 3 times 1 minus alpha 1 square upon 1 minus 3 alpha 1 square. And then you can easily verify that this quantity is greater than 3. So, the tail distribution of ut is heavier than that of a normal distribution. For normal distribution, the kurtosis is equal to 3. And here the tail distribution is heavier than the normal distribution. That is, the shocks ut of a conditional Gaussian arc 1 model is more likely than a Gaussian white noise series to produce outliers. A distribution which has heavier tails means there is more probability that you get an observation in the tail area, and if you are having an observation in the tail area, you may consider that observation as an outlier. For Gaussian arc 1 model, it is more likely than a Gaussian white noise series to produce an outlier. Now, weaknesses of arc models. The model depends on the squares of the previous shocks, and since you are taking the squares of previous shocks, the positive and negative shocks have the same effects on volatility. For example, arc 1 process depends upon ut minus 1 square. So, any positive change in ut minus 1 or negative change in ut minus 1 of the same magnitude have the same effect, but in practice the price of a financial asset responds differently to positive and negative shocks. If today the share price of some commodity suddenly increases, then its response for the next period may be different than if the share price of that particular company or decreases by the same magnitude today. Then the arc model is rather restrictive. For arc 1 model, you require the condition that alpha 1 square lies between 0 and 1 upon 3, or alpha 1 lies between 0 and 1 for the finite fourth moment or for the finite second moment. The constraint becomes complicated for higher order arc models. Actually, that is why I have not considered here arc models of higher order. For those models, such kind of conditions are even more complicated. Then it limits the ability of arc models to capture excess kurtosis. Then often over predict the volatility as they respond slowly to large isolated shocks to the return series. This is another problem with arc models. These models often respond slowly and often over predict the volatility of the process. They respond slowly to large isolated shocks to the return series. That is why they over predict the volatility. Building an arc model, testing for arc effect. Now, suppose u hat t is equal to y t minus mu hat t. You may get this estimated residual by fitting some ARMA model to y t or by fitting some other model for y t, and then we use u hat t square to check for conditional heteroskedasticity using the following tests. Say you may consider Young box test. H naught is the hypothesis that the first m lags of ACF of series u t square are 0. Then Young box is test statistics based on m sample autocorrelations is say q m equal to n into n plus 2 summation j equal to 1 to m rho hat j square divided by n minus j, and this follows chi-square distribution with m degrees of freedoms, and then rho hat j is actually the sample autocorrelation of lag j. Then LM test of Eagle, consider the arc model u t square equal to alpha naught plus alpha 1 u t minus 1 square so on plus alpha m u t minus m square plus eta t. T varies from m plus 1 to n, eta t is error term. We are interested in testing the hypothesis that alpha I is equal to 0 for all I equal to 1 to n. Then these are the steps for the LM test. We run the ARMA or other appropriate linear time series model, and then we estimate the residuals u hat t for t equal to n plus 1 to n. So, first we fit some appropriate model and then we calculate the estimate the residuals, and then you take the square of residuals. So, we square the residuals, then we run the following secondary equation u hat naught plus alpha 1 u hat t minus 1 square plus so on plus alpha m u hat t minus m square plus eta t. So, we run regression here, then the number of lags m can be determined by the span of the data, say 4 for quarterly data, or by any you can use some information criterion also. You choose different lags and then you try to find the appropriate number of lags using AIC or BIC. Then you apply the LM test, which is actually your F test. You have fitted the multiple regression here. So, you get explained sum of square ESS, which is the explained sum of square, you get the residual sum of square. So, your F ratio is explained sum of square minus residual sum of square divided by m. Then LM test of eagle, in which we consider the arc model given here. Eta t is the error term. Then we are interested in testing the hypothesis that alpha is equal to 0 for all I. Then in LM test, first we run some ARMA or other appropriate linear time series model, and we estimate the residuals here. Then we square the residuals. Then we run the following secondary regression. We run the regression for these squared residuals. Again, the number of lags can be determined either using the span of the data or by using some information criterion like AIC or BIC. You try different values of m, and then on the basis of AIC or BIC, you select the appropriate value of m. Then you have run the regression, multiple regression in the previous step. So, your LM test is equivalent to this F test. So, F ratio is you get explained sum of square while running the regression. So, explained sum of square minus you also get residual sum of squares. So, minus residual sum of square divided by m, and then you divide it by the residual sum of square divided by n minus 2 m minus 1, and under H naught this follows F distribution with m n minus 2 m minus 1 degrees of freedoms, and then you can form the critical region for testing this hypothesis. In time series modeling, it is not only the conditional mean of the process, but modeling the conditional variance of the process is also very important. Of course, for a stationary time series, the variance of the process, the unconditional variance of the process is constant. But if you take the conditional variance of the process given the past observation, it may depend upon the magnitude of the past shocks, and it may also depend upon the past variances. Usually in a time series, a big change, whether in increasing direction or decreasing direction, is followed by another big change, and such kind of behavior leads to clusters in variability of the process, and modeling such kind of clusters or such kind of behavior of the time series, such kind of volatile behavior of the time series is important in many fields, like for financial time series analysts or for people who are doing risk analysis. For them, modeling such kind of behavior is very important, and ARC and GARC models are developed keeping in view this kind of volatile behavior. In this lecture, I have considered ARC models. In the next lecture, I will discuss the GARC models for modeling this kind of volatile behavior. So, thank you.